Think about the last time you bought a pair of athletic shoes. You probably checked the cushioning, maybe pressed your thumb into the foam to see how plush it felt.
Oh, yeah, or weighed them in your hands. Everyone wants to know how light they are.
Right. Exactly. But I guarantee you didn't grab the heel and the toe and, like, try to twist the shoe like a wet towel.
Definitely not.
Yeah. We almost never consider the twistability of our footwear. Yet that highly specific metric, the torsional stiffness, it might actually be the single most critical factor in both maximizing your athletic performance and, preventing a catastrophic joint injury.
It really is. It's wildly overlooked.
So today we are doing a deep dive into a rigorous, deeply fascinating piece of scientific literature that isolates this exact mechanism. The paper we are looking at is titled Influence of Torsional Stiffness in Badminton Footwear on Lower Limb Biomechanics.
A very specific title.
Very. And it was authored by Siqin, Shen, Teng, Gusztáv, Fekete, Qichang, Zhao, Fen Yang, and Yaodong Gu. This research was actually published in the Journal of Sports Science and Medicine on March 1st, 2024.
And what I love about this research is that it completely strips away the marketing jargon we usually get with footwear.
Oh, absolutely. No buzzwords here.
Right. It forces us to look squarely at the raw physics of human movement. I mean, we are examining how manipulating a midfoot plate by just a fraction of a millimeter of stiffness fundamentally alters the entire kinetic behavior of your lower extremities.
Just a fraction of a millimeter. That is crazy.
It is. It literally dictates how shock waves travel through your bones. And, it ultimately determines whether a player maintains stability during a rapid movement or ends up rupturing a ligament.
Wow. Okay, so to truly grasp why twisting matters so much, we need to examine the extreme physical demands placed on the human body in court sports.
Which are intense, by the way.
Super intense. I mean, if your only exposure to badminton is like a casual game at a summer barbecue with a drink in one hand.
Right, tapping the birdie over the net.
Exactly. You might think of it as this floaty, gentle activity. But competitive badminton, it involves a relentless sequence of explosive, horizontal and vertical forces.
Yeah, it's basically a series of violent car crashes for your joints.
That's such a good way to put it. Players are executing rapid directional changes, deep, heavily loaded lunges, and abrupt decelerations, all on a highly frictional surface. And because of these intense kinetic demands, 58% of all injuries in this sport occur in the lower limbs.
58%.
Yeah, and mostly in the ankle and the knee.
And the joint torques generated during those abrupt stops are just immense. Like when a player lands from a high vertical jump or violently plants their foot to change direction, the footwear has to manage two entirely competing mechanical demands.
Two competing demands. Okay, what are they?
Well, first, there is the need for flexibility, right? The shoe must allow the natural anatomical posture of the foot to deform and basically adapt to the ground.
Okay, that makes sense.
And this involves accommodating natural torsion, which is that twisting motion between your forefoot and your rear foot. But simultaneous with that need for flexibility is a really critical need for stability.
So it'd have to twist, but not too much.
Exactly. The shoe must physically restrict excessive motion so the ankle doesn't just roll outward under those high lateral braking loads.
Okay, let's unpack this. It is like tuning the suspension on a high-speed sports car for a remarkably sharp corner.
Oh, I like that analogy.
Right. So the athlete lunging for a shuttlecock is the car. If the suspension, which in this case is the shoe, is completely rigid, it won't absorb any of the lateral forces as the car turns, and the car simply flips over.
It just rolls.
Yeah. But if the suspension is too soft and mushy, the car loses its mechanical grip and spins out of control. So, how do researchers objectively measure this specific twisting action in a laboratory setting? I mean, when a human being is moving at full speed.
Well, what's fascinating here is that prior to this study, the scientific community was deeply conflicted on how to even approach this suspension problem.
Really? They couldn't agree?
No, not at all. The core metric they use is foot torsion, which represents the rotational displacement between the forefoot and the rear foot in the frontal plane.
Which basically means?
Essentially, they are measuring how much your heel rotates independently from your toes when you plant your foot.
Right.
Now, earlier studies, like those conducted by Graf and Stefanation, they suggested that stiffer shoes actually increase the torque applied to the ankle, leading to a higher risk of severe sprains.
Okay, so stiff means bad for the ankle.
That's what they thought. But conversely, researchers like Luithi found the exact opposite. They suggested that stiffer shoes reduce the dangerous inversion angles that cause those sprains.
Wait, so the biomechanical data was completely contradictory?
Completely.
Wow. So researchers are faced with this massive injury rate in the sport, incredibly high physical stakes for the athletes, and the scientific literature is pointing in two entirely different directions.
It was a mess.
So to figure out if stiffness fundamentally hurts or helps, I'm guessing they couldn't just have athletes swap shoe models. Like if you have a player test a Nike shoe against an ASICS shoe, you are introducing a mess of uncontrolled variables, right?
Oh, definitely. You've got different foam densities, different rubber friction coefficients, varying stack heights.
And completely different upper materials.
Right. So they had to isolate the twist and literally nothing else.
So how did they pull that off?
Yeah.
By keeping the grip, the foam, and the upper materials exactly the same.
Yeah.
They essentially created identical shoes with 3 different spines to ensure the data was purely about the twist.
That is exactly what they did. To solve that uncontrolled variable problem, the research team engineered a highly controlled environment. They acquired 3 identical pairs of lining badminton shoes, all size US 9.0.
Okay, identical pair.
Yeah. Then they fundamentally altered the internal architecture of the footwear. They customized each pair by inserting different torsion plates made of thermoplastic polyurethane, or TPU, directly into the midfoot.
TPU, that's pretty common in running shoes too, right?
Very common. TPU is this highly versatile polymer that can be precisely formulated during manufacturing to achieve different rigidity levels, but, and this is the key, without changing its weight or volume.
Ah, so the shoe weighs exactly the same.
Exactly. They measured this polymer rigidity using the Shore-D hardness scale, effectively creating 3 distinct isolated spines for the shoes.
Yeah, and what were the 3 levels?
They crafted a 50D shoe, which was highly flexible and soft, a 60D shoe representing a moderate medium stiffness, and a 70D shoe, which was the most rigid, torsionally stiff option.
Wow. So aside from the atomic structure of that internal TPU plate, the shoes were absolutely identical.
100% identical. Then they brought in 15 competitive, highly active male badminton players and mapped their biomechanics with, honestly, clinical precision.
I read about this part. The setup sounds wild.
It is. They attached 38 reflective markers across specific anatomical landmarks on each player. Joints, bone protrusions, muscle insertions.
38 markers on one person.
Right. And this setup was tracked by an 8-camera Vicon motion analysis system running at 200 frames per second.
So capturing every tiny twitch.
Exactly. The Vicon system translates those light reflections into a highly accurate 3D geometric model. It captures the pure kinematics, which is the geometry of the body's motion.
And they were moving on special floors too, right?
Yes. Simultaneously, the players performed movements on specialized Kistler force plates embedded in the floor. Yeah, these plates use microscopic piezoelectric sensors to measure the kinetic impact. Literally, the invisible ground reaction forces transferring between the floor and the foot. And it records that data at an incredible 1,000 frames per second.
That is just a mountain of data. And they subjected the players to 4 foundational movements of the sport to see how the plates handled different types of mechanical stress, right?
Yep. 4 specific movements.
So first, a 45-degree sidestep cutting motion to analyze rapid lateral deceleration.
Like a really hard plant and cut.
Exactly. Second, consecutive vertical jumps to observe how the shoe managed repetitive elastic loading and unloading.
So jumping and landing over and over.
Right. And finally, the forehand clear stroke, looking at both the left foot planting and the right foot driving, which involves a really complex twisting shift of body weight to generate propulsive power.
Right, that whipping motion.
Yeah. So by locking in all the other variables, any difference in the angle of a knee or the force of an impact could be traced directly back to the physical properties of that midfoot TPU plate.
It's brilliant. It provides a crystal clear look into how different stiffness levels alter the flow of kinetic energy through the human body. So, let's look at what happened when they tested the extreme end of the rigidity spectrum. The 70D shoe.
The super stiff one.
Right.
Well, when we look at the ankle joint specifically, the 70D shoe performed exactly as a highly stable shoe is marketed to perform.
Right, it locked it down.
It heavily restricted ankle inversion and rotation. It locked the joint down securely,
Yeah.
physically preventing the foot from rolling laterally. I mean, if you have a history of ankle sprains, the 70D looks like a structural fortress.
It really does. From a purely localized perspective, it is highly protective of the ankle ligaments. But, and this is crucial, the lower limb is not a collection of isolated parts.
Right. It's all connected.
Exactly. We have to view it through the lens of Winter's kinetic chain theory, which was first established back in 1984. The leg is an interconnected mechanical system of segments and joints.
So when one thing moves, everything above it feels it.
Exactly. When a player strikes the rigid court, a massive wave of kinetic energy travels from the floor into the body. Normally, if the shoe and the foot are allowed to deform slightly, the ankle joint absorbs a significant portion of that shock through natural pronation and twisting.
It acts like a shock absorber.
Yes. But a 70D shoe essentially freezes that natural dampening mechanism. And because of the basic laws of physics, that kinetic energy doesn't just vanish simply because the ankle is locked in place.
Here's where it gets really interesting. It's like earthquake-proofing the bottom floor of a skyscraper.
Oh, this is a great way to visualize it.
Right, so you reinforce the lobby to be incredibly rigid. When the earthquake hits, that lobby, which is the ankle in our biomechanical scenario, it doesn't move a single inch. It survives perfectly.
Yep.
But because the lobby refused to absorb any of the vibration, that kinetic shock wave travels straight at the structural columns and forcefully cracks the concrete on the second floor, which is the knee.
That is exactly what happened. The Vicon motion capture data vividly illustrated this exact transfer of force.
What do the numbers show?
When athletes wore the 70D shoes, their kinematic data showed a significantly increased knee abduction angle.
Knee abduction. That's when the knee caves inward, right?
Yes, it's the mechanical inward collapse of the knee toward the body's midline during a heavy load-bearing movement. It happens when the femur twists internally while the tibia is fixed. And the biomechanical literature establishes that increased knee abduction is one of the primary mechanical predictors of anterior cruciate ligament tears.
ACL tears. The career ender.
Exactly. Because the load completely bypassed the rigidly protected ankle, it applied a devastating valgus stress directly to the ligaments of the knee joint.
Wow. So maximum stability for the ankle inherently transfers maximum risk to the knee?
Unfortunately, yes.
So then why would any footwear engineer continue to design a 70D shoe? Or, why would an elite athlete ever choose to wear one if they know it increases the risk of an ACL tear?
If we connect this to the bigger picture, it explains the cruel dilemma elite athletes face every time they step on the court. There are aggressive performance benefits on the other side of that equation.
Wait, really? Benefits to the super stiff shoe?
Oh, absolutely. We have to examine the kinetic data captured by the force plates during the right foot forehand clear stroke.
Okay.
The researchers focus specifically on the vertical ground reaction force, or VGRF. In the 70D shoe, they recorded a significantly higher vertical force, peaking precisely at the 70 to 75% mark of the stance phase.
And just to clarify, the stance phase being the total time the foot is physically planted on the floor.
Right.
So that 70 to 75% window is the critical moment of push-off, where the athlete is forcefully driving their weight back into the court to propel themselves toward the next shuttlecock.
Exactly. And because the 70D TPU plate is so rigid, it strongly resists deformation. In physics terms, it creates a highly elastic collision.
So it bounces back.
Right. Energy isn't lost to the shoe bending or twisting. Instead, the shoe acts as a rigid lever, returning the player's kinetic energy almost instantaneously from the floor back into their upward momentum.
Wow.
This results in a much faster, more explosive push-off, fundamentally reducing the total time spent on the ground. The athlete gains a measurable, split-second burst of speed.
That is wild. So the dilemma is stark. Choose the 70D shoe for that immediate competitive advantage in power and accept the elevated mechanical stress on the knee. Or choose a softer shoe and forfeit that vital energy return.
That is the tightrope they walk.
Okay, so if the 70D is a rigid lever that punishes the knee for the sake of speed, let's analyze the opposite extreme, the 50D shoe.
The softest one.
Right. This was the softest plate, allowing the foot to twist and deform almost naturally without much structural interference.
Very little interference.
And the kinematics showed it allowed maximum ankle mobility in the sagittal plane, meaning front-to-back movement, like pointing and flexing your toes, as well as the horizontal plane, allowing twisting side to side.
And, in certain linear scenarios, that extreme anatomical mobility was highly advantageous.
Really? Like when?
Well, during the consecutive vertical jumps, the 50D shoe facilitated a continuous fluid elastic loading. The foot and the Achilles tendon could operate together like a natural spring without fighting the shoe.
Okay, that sounds ideal.
It is, until you have to move sideways. The moment the movement shifted to rapid lateral deceleration, like the 45-degree sidestep, that extreme flexibility became a severe mechanical liability.
Because the foot just rolls over.
Exactly. The foot experienced dangerous levels of inversion. Without structural resistance from the shoe's midfoot, the lateral ligaments of the outer ankle were forced to independently bear the brunt of the braking forces.
Ouch. Which means the physical risk of a severe lateral ankle sprain just goes through the roof.
Through the roof.
The 50D plate is simply too soft to handle the shear forces generated by rapid court movements. Which I guess brings us to the 60D shoe, the moderate stiffness option.
Right, the Goldilocks zone. The 60D TPU plate functioned not as a rigid lever nor as a flimsy base, but as a dynamic shock absorber.
How did it perform in the cut?
Well, during the aggressive 45-degree sidestep cutting task, the kinematic data shifted dramatically. The players wearing the 60D shoe demonstrated the lowest knee abduction angle among all three variations.
The lowest?
Yeah. The 60D plate possessed just enough flexibility to deform and dissipate the ground reaction forces before they reached the knee.
So it saved the knee.
Yes, minimizing the valgus stress and significantly lowering the risk of an ACL tear. But simultaneously, it maintained enough structural integrity to prevent the extreme ankle inversions seen in the 50D.
That's the perfect balance.
Yeah.
And furthermore, during the left foot forehand clear, which requires a heavy twisting lunge to reach the shuttlecock, the 60D shoe allowed for increased peak ankle dorsiflexion.
Right.
And dorsiflexion is the mechanical action of the shin traveling further forward over the toes. This specific range of motion is crucial for lowering the athlete's center of gravity and absorbing the braking force smoothly over a longer duration, rather than suffering a sharp, jarring impact.
It provided the necessary mechanical compliance for the foot to navigate complex, multiplanar movements safely. It kept the entire kinetic chain operating within tolerable stress limits.
Okay, but wait, I have to challenge this conclusion.
Oh.
We just established that the rigid 70D shoe creates a faster, more explosive push-off because it acts like a stiff lever.
Right, the speed advantage.
Exactly. If I am an insanely competitive athlete, my career and my livelihood rely entirely on outpacing my opponent. Even if the 60D shoe protects my knee and ankle, aren't I sacrificing vital speed by wearing it? I mean, how does a designer convince them to wear the 60D? How does the biomechanical data justify giving up that performance edge?
It's a great point, but the data actually reveals that the 70D's speed advantage is highly situational, not absolute. Yeah. While the 70 did generate higher vertical ground reaction forces during the specific push-off phase of the forehand stroke, the 60D actually recorded the shortest total stance time during the 45-degree lateral cutting task.
Wait, the 60D was faster in the cut?
Yes. When the athlete needed to rapidly plant the foot, decelerate the body's mass, and change direction, the moderate stiffness of the 60D allowed for a more efficient biomechanical transition.
That makes total sense, because the foot could actually roll through the motion.
Exactly. The extreme rigidity of the 70D actually hindered the foot's natural ability to quickly roll through the lateral braking motion. So the 60D isn't purely a compromise for joint safety.
Right.
Depending on the biomechanical demands of the specific movement, it can objectively outperform the stiffer shoe in agility and quickness.
That is incredible. It fundamentally challenges the deeply held assumption in sports that stiffer and more aggressive equipment automatically translates to better athletic performance.
It really does.
So what does this all mean? Obviously, for anyone playing high-impact court sports like badminton, tennis, or basketball, this research forces a total reevaluation of how you select your equipment. But the implications stretch far beyond elite athletics, don't they?
Oh, everywhere.
Whether you are running on pavement, hiking rough terrain, or just navigating your daily routine, you have to consider the kinetic chain.
You really do.
A rigid boot that makes your ankle feel completely locked in and invincible is fundamentally altering how your body absorbs physical shock. That kinetic energy does not disappear. It travels upward. Your footwear dictates the mechanical stress placed on your knees, your hips, and your lower back.
And, this raises an important question about the future of biomechanical engineering. Currently, we are looking at a static variable. A shoe is manufactured to be either 50D, 60D, or 70D.
You buy it, and that's what it is.
Right, but the kinetic demands of human movement are entirely dynamic and constantly changing.
So where are we going with this?
The logical next step from this data is the development of active stiffness materials.
Wait, like materials that change on the fly?
Exactly. Imagine a midfoot plate engineered with smart polymers that alter their molecular rigidity in real time based on the applied load.
Oh, wow.
right? It functions as a compliant 50D while you are jumping to allow natural flexion, instantly stiffens to a 60D to act as a shock absorber and protect your ACL as you cut laterally, and then hardens into a completely rigid 70D lever a millisecond later to maximize your explosive push-off.
That is mind-blowing.
That dynamic adaptability is the exact horizon this kinematic data is pointing toward.
A shape-shifting, responsive structural plate that adapts to the demands of your kinetic chain mid-stride. It sounds incredibly futuristic, like science fiction, but the biomechanical data clearly proves exactly why human joints require it.
The math demands it.
Exactly. To fully grasp the intricate kinematics involved and to explore the detailed range of motion graphs detailing how forces flow through these joints, we highly encourage you to read the full article by Shen and colleagues. It is an exceptional, accessible piece of rigorous scientific literature.
Highly recommend it.
And please, make sure to follow our channel and turn on your notifications so you don't miss our future deep dives into vital scientific research. Next time you are lacing up your shoes, give them a twist. Remember the kinetic chain. And remember that sometimes allowing a little flexibility at the foundation is the only way to protect the structure.